Good time of the day, everyone, and welcome to the series of online technology meetings provided to you by EPIC. And today we discuss the exciting topic of photonic computers and artificial intelligence. Let me remind you first that EPIC is the largest photonic industry association in the world. It includes over 800 corporate members in Europe and also all around the world. And today we have an exciting agenda completed with 8 speakers, and we'll start with a presentation from IBM Research and follow up by another scientific presentation from Zurich University of Applied Science, followed up by our industry members such as Akitonic, Rotonium, Ipronics, Nanoscribe, and Quantex Security Encoding, all of them talking about photonic computers and AI applications. So this is very exciting. I'm looking forward to hear to all of our speakers. Before we start, also let me mention the great audience we have registered for this meeting. So as you can see here, there are many companies that will follow up our meeting and participate in the discussions from all levels of the value chain, starting with the software and design and R&D entities, going to contract manufacturers, component and model producers, metrology and testing, equipment manufacturers, providers of services, and of course our end users and system integrators. So this is very exciting. I'm looking forward to the discussion. And without further delay, I'm glad to invite our first speaker in the keynote of this session that will enlighten us about the photonic computers. So Bert Jan Offrein, the manager of Neuromorphic devices and systems at IBM Research, and also a professor. Welcome, Bert.
Thank you, Ivan, for the opportunity to give this presentation. Let me share my screen.
Go ahead. The floor is yours.
Yeah, just sharing my screen. Good, perfect. So thank you very much for inviting me to give this presentation at this EPIC event. And I will talk about, say, computing for AI. And I will try to highlight several aspects of this. Indeed, as Ivan mentioned, I'm 100% IBM, but also have an affiliation with the University of Twente in the Netherlands, as you see indicated below. So I would like to start, let me see. Yeah, I would like to start with this picture. It's Roadrunner, the first petaflop supercomputer. It was built by IBM in 2008. So why do I show this picture? The interesting thing is, if you look at today's AI applications and the neural networks that are behind, and especially the training of these systems, then looking at the y-axis, where you see the compute effort in petaflop second days and the evolution of these kind of systems over time, the x-axis, you see that today these AI networks, neural networks, need 10,000 days of a supercomputer that was installed the first time in 2008. This to indicate what a tremendous compute effort is related to optimizing, training the neural networks that we have today. You can look at, say, 2008. That's a long time ago. Probably it depends on your age, how long you think this is ago. I think it's not so long ago. So already that was a really strong supercomputer in 2008. And now we need 10,000 days of such a computer. So what are these computations that are required? If you look at the neural network, where in the picture you see these blue dots that are neurons, nonlinear activation functions. They are arranged in layers and are interconnected. On the interconnections, these lines, you see these yellow dots that are the synaptic weights. And in the end, in such a system, the neurons are all the same, the nonlinear functions. And the functionality is determined by the interconnections and the strength of all these connections. So in the end, the values of the synaptic weights. Now, if you look at one neuron, it will receive signals from all the neurons in the previous layer. And each signal is weighted. That means the signal is multiplied with value, so that's a multiplication. And then all these multiplied values need to be added together. In the end, that is a multiply accumulate. And if you do this not for a single neuron, but for the full layer, this turns into a vector matrix multiplication. Now, the compute effort of a vector matrix multiplication scales with the number of neurons. And of course, you also have the calculation of the nonlinear activation itself, which clearly scales with the number of neurons. Whereas the vector matrix multiplication scales with the number of neurons squared, the square thereof, should have said. So clearly, if the size of these networks is increasing so tremendously, as we know that they do, with billions of parameters, it's clear that the vast majority of the compute that is required is, in the end, in vector matrix multiplication. So this is the thing that needs to be enhanced and made more power efficient in order to make the overall compute more powerful. Well, this is currently going on, this whole trend, with existing hardware. And what's happening is that transistors continue scaling. Say, some time ago, there was the feeling that Moore's law is going to end. Well, it did change in the fact that, say, the standard Dennard scaling is over, but currently transistors continue scaling by adding in new geometries and new materials. We have the memory, that is, say, on the one hand, as you see on the right-hand side, memory and storage, as for example, DRAM, or maybe hard disk and so on, but also the memory that is on the chip itself, like SRAM, the logic functions and the circuits, in the end, for example, to do the vector matrix multiplication. And as I said, all these things continue scaling. Transistors continue scaling, memory continues scaling in terms of, say, the amount of transistors per area, the amount of memory, say, capacity. And what's also changing is that the memory is assembled closer and closer to the point where you do the calculations in the accelerator or in the CPU. So in the past, as you probably remember, memory was integrated as these vertical DIMMs on a compute board. Nowadays, memory is integrated as an HBM, high bandwidth memory, which is a vertical stack of DRAM, 3D integrated, directly on the same carrier substrate as the CPU or the GPU or the other accelerator. And the other thing that is happening, of course, to continue to scale the system is the communication between all the parts of the system, higher connectivity bandwidth at all levels. And here optics is playing a more and more important role. Nevertheless, while all these trends continue going, there is a discrepancy that is appearing. And that's what I want to show here. The important discrepancy is that the compute in flops, as you see indicated in the graph on the lower right, is scaling still much faster than the communication bandwidth, for example, to memory or the overall interconnection. So the compute effort is scaling as 60,000 times last 20 years, the memory bandwidth 100 times, and the interconnect bandwidth even less. So there is a change, a shift in the overall architecture. And this needs to be tackled. Let's look back to 2011 related to optics. As this is an optics conference, this is a slide I was showing in 2011. And what you see indicated here is a compute board with processors, with memory. In 2011, this was this vertical memory, and the way how optics is integrated. I started with 2008, which is again this Roadrunner system, because this was not just the first petaflop system, it was also the first system where optics was massively integrated by plugging it at the edge of the card as pluggable optics. Then in 2011, IBM built a system called PERCS, which was a supercomputing system where optics was integrated not just at the edge of the system, but in the system itself on the processor package, as you see indicated there. And at that time, long time ago, I would say, we already had a roadmap to continue this integration of optics, going to a deep integration of optics on the processor package, the communication in the board, in the backplane, and this trend moving forward, going maybe from, say, VCSEL-based systems to silicon photonics and so on. In the end, a trend of, say, bringing optics closer, the integration of optics closer to the way how we are integrating electronics already, right? But what happened? Nothing. In the end, this system in 2011 was a massive exploration and also demonstration of the capability of optics, but the integration thereof in compute systems at that time was viable for a supercomputer, but too expensive for standard systems. So this whole trend at that moment did not happen. But now we are in a different situation with the whole scaling of compute requirements related to AI. So this whole story of bringing in optics in the system for communication is coming back. And IBM is working on this. There was a press announcement last year. The important thing here is that we need to learn from the past and bring the optics in such a way that we overcome the massive overhead that optics used to bring in terms of, say, assembly, number of components, fiber handling, and so on. And one way how IBM is tackling this is by enabling a direct, dense optical I/O and fiber coupling to a silicon photonics chip with a polymer waveguide interface, as you see indicated here. Now, if we do this, this will help continue scaling compute systems. But we will not come around the standard bottleneck that we have, which is the von Neumann bottleneck, that if we do not change the compute architecture, we continuously need to move data from the processing unit to memory and back. So looking at this, say we have main memory, like DRAM, local memory, SRAM, the processing unit. If you look at, say, the energy it takes to bring the data from main memory into the processing unit, what you see here is that it's especially the transfer of data between main memory and the local memory that takes most energy. So this is something we need to try to get around. And this is where in-memory computing and analog AI is coming in. We want to go to a situation that you see on the right-hand side. And I explain it here, first of all, in the electrical domain. We want to do signal processing in a way that resembles more the actual calculation in a neural network. And imagine you have, for example, a resistor. You apply a voltage over a resistor, then the current you get is the voltage times 1 over the resistance, so the conductance. You can do this for one resistor or for a lot of resistors, and then take all these currents and bring them together to one output. And in the end, you use then Ohm's law and Kirchhoff's law to do exactly the calculation that we know from the neural network. And in this case, the compute effort does not scale with the square of the number of neurons as in the digital case, but it's in this analog case, it scales order 1. So whether we have just a few resistors, a few synaptic rates, or a lot of them, we apply the voltages and we immediately get the output. Now, you can do this in the electrical domain, and I will say a little bit more about that, but also in the optical domain. And say a similar approach you can think of, for example, the reflection of a light beam on a mirror. The output is the input power times the reflection, that's the multiplication. You can do this with many mirrors and many beams and bring all the outputs onto a detector, and you have the same kind of effect. Important, if you do this, is that you need to resemble the full architecture of your neural network into the hardware. But should avoid to reprogram this, say, analog structure, because then you would still need to read data from memory, reprogram, and so on. You want to say map the full neural network into the hardware, as you see indicated below, because this way data can nicely flow through without any memory access, because the data is coming in, you have all these synaptic rates already programmed in your accelerators, in your analog accelerators, and you massively avoid actual memory access compared to the digital case. And this way you can run several orders of magnitude for inferencing neural networks and for training even more. So the whole system then looks roughly like this, much simplified. Now, how do we do these accelerators in the electrical and in the optical domain? In the electrical domain, it is clear that there is this architecture, as you see indicated on the left-hand side, which is a crossbar array, where you have these lines that are, say, conductive lines, copper lines, integrated in the back end of line of a silicon process that are crossing. And at the cross points, you have this resistive element. Now, the important thing is that this resistor must be programmable to the value that you need related to the synaptic rate in the neural network. So you need a memristor. That's a device where you can set the value of the resistance with, say, a larger voltage, 1 to 2 volt. And when you read it out at 0.1, 0.2 volt, it doesn't change. So it's a non-volatile resistive memory that should be able to take multiple resistance levels. Well, there are various technologies available here. What is clear is that it's always this crossbar type of architecture, the different technologies to realize the memristor, like phase change memory, resistive RAM, ferroelectric RAM, and I will give you an example. In integrated optics, it looks slightly different. You can use different kinds of integrated optic architectures, circuit layouts, in order to build this kind of functionality. On the left-hand side, you see a crossbar, similar as in the electronics. You can also do this with a kind of Mach-Zehnder interferometer structure, or with a diffractive element, as you see fully on the right-hand side. I will say more about this later. Let's first talk to also say compare what optics can do with what electronics can do. Let's first have a look at an example of the electrical situation. We have been working at IBM on resistive RAM devices that are, as you see indicated here, metal, insulator, metal kind of structures. The metals in the structure are this titanium nitride layers. And in between, we have a thin hafnium oxide layer and the titanium layer as a kind of base technology that has been known for a long time. And if you have realized this structure, in the beginning, the resistance is very high. You apply a voltage in order to get a controlled breakdown and create a conductive filament in the hafnium dioxide. That's indicated with this red line. The issue of this standard technology is that you get this conductive state, you can reverse the voltage, and you can then open this conductive filament again by getting tunneling. So you go back to high resistance, but because it's a tunneling related effect, this is something that is very stochastic and very strongly depends on the actual configuration of your atoms in the whole structure. What we've been working on then in my team at IBM is that we have replaced this titanium layer with a metal oxide layer. The idea here is that this conductive filament is in the end is a line of oxygen vacancies. And these the oxygen goes into the titanium on the standard technology side. What we were hoping is that if we have a metal oxide where if the metal oxide is more metal-like, you have a high conductance. If it's more oxidized, you have a high resistance. Maybe we can say make this technology this way more gradually changing the resistance by step oxidizing or reducing the metal oxide layer. So we've realized this type of technology, and what you see indicated here is that indeed this is the case. What you see indicated in the graphs at the bottom is that we have the technology, we have formed these devices in such a way that you can actually switch the resistance. So we have already created this filament. And then we come in with a series of either positive or negative voltage pulses. You see on the left-hand side that for the standard technology, you have a very stochastic kind of switching behavior and very abrupt switching from a low to high resistive state. In our new technology, this is much more gradual. And on the picture fully at the right, you also see that if we stop the, say, providing the positive or negative voltage pulses at some point and just measure the resistance over time, that it does stay very stable. So indeed, we have here with this new technology, we have something that is capable to represent a large range of resistances, so a large range of synaptic weights, which is non-volatile, exactly what we need for the inference, but even in this case, also for the training of neural networks. We have optimized this technology further. We have transferred this technology also to IBM Albany, which is a kind of development foundry from IBM in the US. And what you see indicated here on the in the second graph is that we are now able, after optimizing this technology, to program up to 35 levels. They are nicely stable over time. And we have also, in the graph on the fully right-hand side, we have looked how these kind of resistances behave over time, extrapolated up to 10 years, and we see that we can store up to 10 levels, resistance levels, even after 10 years. Now, what is important with this type of technology is that it is very, very dense. We can scale these devices down to 70 by 70 nanometer. They are integrated in the back end of line of a standard silicon process, so you can directly combine this kind of functionality of doing these calculations, the vector matrix multiplications, with CMOS electronics that's integrated in the front end. So with these kind of structures, you can, in the end, realize a fully mapped neural network in hardware, as I've indicated before, on a silicon chip. We have demonstrated through simulation that this technology can be applied. This is a collaboration with the University of Eindhoven and BMW in the EU project Fast Track, that we can use this technology for example, gesture recognition, for human car interfacing. We can use it for training neural networks as well as for inference, and that the accuracy that we get is roughly the same as using floating point digital technology. So that's the electrical side. Let's have a look at the optics. So as indicated, there are several options in the optics, and I want to show you a few examples. One is to do the crossbar directly in the optical domain. You can do this, but different than in electronics, where you can bring together two currents and they nicely add up, Kirchhoff's law. In optics, this does not work. Because if you try to combine signals, you always have an interference effect, and in the end, you will lose a factor 1 over n. If you want to couple in light, also light will be coupled. So this is an inherent challenge of these kind of structures. So we have realized these kind of designs and we've tested, and this is all working, but there is a scalability issue, because when you lose 1 over n of your power, it's very hard to scale these kind of matrices. So from that point of view, doing such an interference kind of option, a coherent situation, as indicated here, using such a, say, Mach-Zehnder interferometer kind of structure is much better. But here in the end, you run into challenges because the number of heaters that are required scales up quickly, or heaters tuning elements to set the interference conditions scale strongly with the number of inputs and outputs. So here in the end, you run into a challenge in terms of, say, the complexity to control the system. What we did is that we've realized a simplified version of this, not a two-dimensional kind of interferometer structure, but more a one-dimensional. It's a cascade, linear cascade of Mach-Zehnder interferometers, as you see indicated below. And if you use such a structure in the time domain, you can build a convolutional signal processor. You see more details here. What happens is that we have a cascade of, say, tunable couplers, tunable delay lines, and if light is coming in, for example, from an image, you have the first pixel, the second pixel, data is coming in a time sequence. If the first pixel value, the part of the light that is going through the long arm, will meet the second pixel, the light fraction thereof that is going through the short arm in the delay line, you get an overlap. And this way you can in the end do a convolution, because this is a finite impulse response filter, which is in the end representing a convolution. And convolutions are very important in neural networks. So this type of device can in the end do a convolution for neural networks and convolutional neural networks. For example, for, as I indicate here, for edge detection. We have realized these devices in silicon photonics. And by doing these operations, as you see on the right-hand side, if we have a signal that's coming in that is increasing the blue line over time in strength, the red line is the output, and you see that we can detect the edges and in the end, in an efficient manner, get an operation that is important for neural networks. If you now do the calculation on the efficiency, as you see indicated here, taking into account the full system, the laser, the modulator, the data that needs to come in, the driver for the modulator, the photonic processor, including, say, all these Mach-Zehnder interferometers that need to be tuned to the right value in order to represent the operation you want to do, the detector, amplifier, and so on. Also taking into account the full optical power budget to make sure that in the end we are really able to detect the signal at the end with the required accuracy or resolution. If we take all these things into account, we come to an overall efficiency of this device of roughly 2.5 teraops per watt, which is an interesting value because it's roughly the same type of efficiency you get for digital systems. So it's not inherently by using this kind of analog approaches that we massively win. So does this now make sense? The answer is, in order to win in power efficiency, in this case, not directly, but this system can do something that digital systems or electrical analog systems cannot do, in the sense that we can handle ultra high-speed signals. We can also reprogram this system, say, depending on the tuning elements that you use in a very fast and very accurate manner. So depending on the application, this is certainly something that can find a path. In the last few minutes, I see that my time is slowly coming up, also leaving time for questions. In the last few minutes, I want to say something a little bit about, say, applying optics for training neural networks. The application I just gave is for inferencing, the convolution calculation, but can we also use optics for training neural networks? The difference between inference and training is that in the inference case, you want to set your synaptic weights to a dedicated value, and it should stay there. Whereas if you do training, you are continuously optimizing your synaptic weights until your neural network is doing what you want it to do until the error is minimized. Now, to do this in an efficient manner, these kind of crossbar structures, as I've explained before, are very efficient means, because you can do the forward calculation, just the inference operation, as you see indicated on the left-hand side in blue, as well as if you do the backpropagation algorithm, you can also do the backward calculation on the transpose of the matrix using the data in red, where you propagate the error back and you do the vector matrix multiplication on the transpose of the matrix. And you do this with exactly the same structure. So another important aspect here is that you change the values of your resistances just by applying the inputs at the of your signals at the two inputs that you have in your system. So, for example, X and WX, you just put them in. So, in the end, you use also just say order n signals to change n square weights. And the question is, can we do something similar in optics? And A photonic crossbar using diffractive structures is what you see on the right-hand side. Assume we have a medium where we can write in a certain corrugation of the refractive index in such a manner that we have are able to do, say, a diffractive coupling of an input to an output, and then also tune this diffractive coupling efficiency. This can be done using the photorefractive effect. The photorefractive effect, as you see in the center, is a nonlinear optical effect where, in the end, through the excitation of carriers and a redistribution thereof in a medium, you're able to store a synaptic weight in the optical domain, because this material also has, say, an electro-optic effect that in the end transfers this redistribution of charge carriers in a change in the refractive index on which you can do the synaptic weight operation. So this is not new. This is something that people already did a long time ago in the 90s. Now, with integrated optics, we can do this in, for example, silicon photonics. The thing is, we need to integrate a photorefractive layer. We've done experiments here, just finalizing, using, say, different types of materials, building these structures, as you see indicated. We have demonstrated this effect on gallium arsenide, and we are currently exploring how to bring this further. The experiments we did here is showing that we can do the synaptic operation using 2 optical inputs. We need to scale to more. That's what we are currently going towards. And I would like to finalize in the end with, say, a comparison with all these operation circuit layouts. The crossbar, where you have the input, where you have the loss issues with scaling 1/n. The interferometric structure, where you have a scalability challenge because you just become too complex in controlling the structure, or a diffractive structure, as I just indicated, where we believe in principle you can scale to a much larger number of inputs and outputs. And the latter is important because if you have many inputs and outputs, that means that you have a lot of calculations between the input and the output, and your, say, base effort in terms of, for example, power, that you need to give in always the laser and the detector, the amplifier, and so on. That is a given that you have. If you can do more calculations in between, you win in efficiency. And based on our calculations, if you are going to a large kind of crossbar in the analog domain, you can actually win. So with this, I would like to conclude stating that electronics has an advantage in terms of scalability, going to very dense structures. Optics is good because you're able to handle very high-speed signals. And depending on the application, you have to see what makes most sense. With that, I would like to thank the team and thank you very much for your attention.
Great. Thank you very much, Bert. Great presentation, and you did a great job setting up the stage for our future discussion, I believe. Yeah, let me tell everyone in the audience that so after each presentation, we'll have time for a few questions. So you can also now prepare your question for Bert. For this, you just need to push the raise hand button at the bottom of your screen. So I pass you the word. And yeah, while you think about it, I wanted to ask you, Bert. So you outlined all these options that can be done with photonic computing and how it compares to the electronic computing. I'm wondering, so because all of these exciting developments are happening at IBM, is there some grounds for collaboration with IBM for our members? Is there something that the members of our community could offer you, maybe in terms of building the interconnects, in terms of the photonic integrated circuits, something where our community could help you?
Oh, sure. Thanks for the question. So we are very well integrated, I would say, in the also European landscape of, for example, EU projects. I mean, that's the easiest way to collaborate, of course. Where, to some extent on these technologies, we do the design and the characterization, but others provide the chips, and maybe others provide again, say, the packaging. So we are very open always to discuss potential interactions. Yes.
Okay, well then I guess the audience of our meeting can reach out to you using that email you showed.
Yep,
and,
sure.
Okay, that's great then. Any more questions from the audience? Okay, I see there's one from Bruno from ETH Zurich. Go ahead, Bruno. You just need to unmute.
Okay, can you hear me now? First, thanks for the presentation. My question is, so you showed different methods, if I understood correctly, to realize matrix multiplication, right?
Yep.
How would you implement then a non-linear activation function in this case?
Yeah, excellent question, because I did not really discuss about that. So, because the main our challenge is in doing this vector matrix multiplication. Our approach currently is such that we want to do the vector matrix multiplication in the analog domain, as with the technology concepts as I demonstrated, but the nonlinear activation is done in the digital domain, just with standard CMOS technology. This means, of course, that you need analog to digital and digital to analog converters at the interfaces. This is taking power, yes. On the other hand, by doing this transition, you are also making sure that you always kind of, say, reset your signals in such a way that you can use them for the next stage, going into the next analog accelerator, right? And still taking this all into account, we still see that there is the benefit, as I've indicated, in terms of overall power efficiency.
Okay, thank you.
Okay, great. If there is no further questions, I actually suggest that we catch up a little bit on timing. So let me thank Bert again for
Thank you.
Great keynote. And now we have a great person also to follow up on what we heard from Bert. And this is Yulia Sandamirskaya, also a researcher, the head of a research center at Zurich University of Applied Science. Hello, Yulia. And I think she will follow up with a more of a life science point of view on photonic computing.
Let's see, a mixture probably. Hi, Ivan. Thanks a lot for the introduction. Hello, everyone. Thanks a lot for the invitation. I think I'll start without further ado because the slot is dense and I have a couple things to say. So my talk is focusing on the neuromorphic computing. There only will be a little bit mentioning optical computing. So I will give a brief overview of this field. I think the term pops up again and again, probably in your community as well. So I think it might be useful to define the terms very clearly. So I like to do that. And then I will go in a little bit more depth in actual neuromorphic computing, which is a bit less about hardware. It's a bit more about algorithms. And this is where I think the most obvious overlap is, because when we're looking for certain algorithms, we do look for hardware support, and I can see how photonics and optical computing could be helpful there, and also could kind of show the directions in which the hardware could be developed. And I do want to go beyond matrix multiplication only for the future of computing. Okay, so neuromorphic computing hardware. Let's start with a very practical, pragmatic definition. You might hear people arguing about what is neuromorphic computing hardware exactly. So I will define it in the following very inclusive way. So it's some parallel computing substrate with a lot of cores or some computing units that work in parallel. Typically, these hardware will be proud to have memory and processing tightly integrated one way or another. So either have a digital device and it has a lot of local memory very close to processing, or you have an analog device or a mixed signal device where memory and computing are one and the same thing. So this is one very important feature of neuromorphic hardware that is probably the key element for its power efficiency. And another important element is clockless, asynchronous, and event-driven processing that puts it in contrast to other computing devices, such as a CPU that always has a clock, and every clock cycle something needs to happen, or a GPU, the input comes in and an image or some input vector comes in, it triggers computation, and then there's an output produced. And neuromorphic hardware typically supports this asynchronous processing, where different processes can run on different parts of this hardware at their own pace. And not much processing might happen for quite a while until some interesting event is detected, and this is when processing is happening and power is consumed. The technology that is used to develop this neuromorphic hardware can vary. And I will go touch a little bit upon some of these technologies. So it can be mixed signal, analog digital, VLSI technology that can use something known as memristive devices. In-memory computing is also often listed under the label neuromorphic. And then you can have more conventional digital computers. You can have more or less conventional processors arranged in an array in such a way that it still can carry the name of neuromorphic computing. And optical computers could also be called neuromorphic. But the term itself, neuromorphic, what does it mean? So it means brain-inspired. So it's computing that is inspired by biological brains and neural systems. And when I say biological brain, I not only mean the human brain, which is of course an amazing device, but also brains of simpler animals. I always like to show these examples of, some hummingbird that has a brain with only 1 million neurons and can already produce amazing behaviors. Or like even more extreme, like the brain of a Drosophila fly, this teeny tiny fly that can recognize smells, can distinguish eatable, not eatable things, can follow, the route, can fly around, only has 100,000 neurons. Like imagine, really compact, really efficient system. So all this neuromorphic computing is the brain-inspired computing. So I will start with a little historical overview. So historically, the first neuromorphic computers were mixed signal VLSI ones. And they were following a bottom-up approach. What does it mean? The brain is fascinating. People who are electrical engineers, like the Kava Mead, one of the founders of this field, they, recognize that brain is fascinating. Brain consists of neurons and synapses. Let's try to emulate those in electronics. So, they talk to biologists and they try to understand a little bit better. So what are these neurons in the brain are doing? They appreciate it. Brains are complex cells. They have something called soma, which seems to integrate incoming signals. The incoming signals seem to come in the form of spikes, so discrete pulses. So nothing in between, and then a pulse comes, and this pulse can be communicated from cell to cell, and not the kind of continuous signals. So the soma integrates those signals. If the activation reaches some threshold, the soma produces a spike as well. And in between, there are some exponential decays that are happening, and integration also has some exponential curves, which Carver thought we can model those with electrical circuits. And then in biology, neurons seem to be, in most cases, connected by something called synapses. Synapse is actually a gap between two neurons, and this gap can be filled with some neurotransmitters and charged molecules that transmit electrical signals from one cell to another cell. And in biology, the synapses have an interesting property, namely plasticity. So they change like all the time. They can get bigger and smaller. So the connection between the two neurons can get stronger or weaker based on the activity of the two connected neurons. So a very interesting property that just fascinated the people. And yes, so both these properties can be, in principle, modeled with very simple electrical circuits. Now, you can represent the charge on the membrane of a neuron with a charge on the capacitor, and you can have some mechanism that compares this charge to a threshold, and then if the threshold is reached, something might happen. So people tinkered around a little bit and came up with a scheme that allowed them to implement a pretty sophisticated model of this biological neuron. It would have the behaviors, the exponential integration curves, and then comparing to the threshold spike, then the reset period, the refractory period when the neuron cannot receive new input. and could model a whole range of biological behaviors. Quite fascinating. They could also build the plastic synapse, so they could build this connection between two neurons that also will have the dynamics that depends on activity of the neuron before the synapse and after the synapse in a very similar way to biology. I will not show you all the curves, but just trust me, they mimic the behavior of biological neurons pretty faithfully. And they managed using, VLSI, very large integration technology, managed to put fairly large number of these neurons on a chip. So this is, for instance, the Rolls chip from around 10 years ago with 256 neurons, with all-to-all connectivity, potentially, with half of the connections non-plastic, half of them plastic. You can use this analog device as a computing device. In this field of mixed signal or analog electronics, there's a trend recently to try to replace, some large chunks of these schematics that are, for instance, responsible for connections between two neurons with memristors. So as you might know, memristors are materials that have this nice property that they can have a resistance that can be changed by typically, some electrical pulses, can be changed and then can be retained. So it's a very nice compact model of a synapse. Something happens, you change your resistance, you changed your connectivity strength, let's say, between two neurons, and then it's kept like that in a non-volatile manner somehow. So here's the list of, from one of the review papers, a list of a couple technologies that allow you to achieve this behavior. It's either based on some filaments that can be built, like filaments of atoms that can be built between, the top electrode and the bottom electrode, changing the conductivity of the device. Some systems use some amorphous materials that can be in the crystalline form or amorphous form, and that changes the conductivity. There are some systems based on some spintronics or ferromagnetic materials, where again you can control the conductivity of a material. Leading to very compact devices. As we just heard from Bert, these compact devices can be used in a crossbar array that allows us to do a very efficient matrix multiplication. Or you can also use these devices in those neuromorphic chips that mimic these biological spiking dynamics. So as the ETH colleague just asked about the nonlinearity, so the solution today is that the memristive devices, they don't provide the nonlinearity. The nonlinearity is provided by neurons that can be implemented with the CMOS technology, in analog technology, and which can be interfaced to the memristive technology. So if one would want to have a combination of memristors and spiking neurons with their nonlinearity, one can do that. Typically in this neuromorphic or spiking chip, you wouldn't use it for modeling very deep networks. You would rather have a simple network with only a single layer of learning or plastic synapses. The advantage is that this learning can be continual, so you can continue learning. You don't need to have a training fashion where you slowly converge your very deep network to some solution, but you can have continual learning with memristors. Yeah, here's an overview of development of this memristive technology in the last 30 years, overlaid with the development of large-scale neuromorphic systems, and I will mention some of them in a moment. And today in the research, right, so there are these emerging concepts for computing going beyond CMOS, and this is where photonic come into play as well. To replace those memristive devices. And this is one of the schematics, but I think Bert has mentioned how the photonic processors can be used to do this matrix multiplication-like operations in an accelerated fashion. Right, so this was the bottom-up approach, the historically, how neuromorphic hardware came into play. Fascination by the brain, trying to build the elementary computing units from the brain, and then try to scale up a little bit and then see what happens. Now, in digital, we can see what happens a little bit faster, because in digital technology, it is easier to build a computing system that looks somewhat like a brain. So these are some examples. Intel's Loihi chip, the Spinnaker system from the Human Brain Project, large European project. This is a spec system from SynSense. This is a startup, a spin-off from the University of Zurich and ETH that combines event-based neuromorphic camera with computing chip. And this is an interesting plot that I would like to highlight. This is a plot made by Intel at some point. It compares the energy consumption of Neuromorphic Loihi chip to a bunch of other technologies. So, some of them are GPU, a CPU, NVIDIA, so the GPU, or, my video's accelerator. And on the y-axis, it compares the solution time ratio, so how fast the solution was found and how much energy was spent. And it's always compared to the Leahy. So we can see, it's all over the place. This is the parity line. This is where they're equal. And there are some cases where actually on the neuromorphic chip, the workload would run worse than on a conventional GPU. And those are mostly those deep networks that everyone is so excited about these days. But there are some workloads which are in this corner where we get advantages from this technology in orders of magnitude. So 5 orders of magnitude advantage in terms of energy and 3 orders in terms of time. And most of these workloads, they are some kind of recurrent networks. That can be, some k-nearest neighbor search network. This can be some optimization network. This can be some simultaneous localization and mapping network. So not deep networks. And this is, I guess, the main message from my talk. When we talk about neural networks and neural networks accelerators, it doesn't have to all be about deep networks only. And this is what we learned with these digital chips. So this is now a zoom in on the Loihi chip from Intel. The first version of it features 128 neuromorphic cores, supporting a bunch of neurons and synapses, complex neural network topology. So I can wire up my neurons however I want. They don't have to be arranged in a layered structure, don't have to be convolutional, don't have to be transformers. Can have little circuits in one place of the neuron, some larger circuit in some other place of the neuron. Has on-chip learning, so all the connections, they can change live on this chip, and it's fully asynchronous. Okay, so when I have this chip, and I had it in my hands, right, at Intel, so the question is, how do I program it? And now if you look at the algorithmic frameworks used by people, the deep learning will, of course, dominate the scene. Why? Because it's so easy to use. You have your network trained easily with 5 lines of code. There's abundant data, abundant tools, abundant benchmarks to compare your algorithm. But is the deep learning the only framework? No, it's not. So I'll just quickly swap through other examples. And if you're curious, we can either talk about that or you can just look up yourself. We have optimization problem solvers, which run on these neuromorphic chips very efficiently. We have a bunch of bio-inspired circuits. We have some conventional algorithms that can be translated into a form compatible with neuromorphic chips. And we have particular frameworks like dynamic neural fields or vector symbolic architectures or algebras that can run on them. Okay, so just a flash for the example. Optimization networks, right? So either graph search tasks or, optimization tasks such as combinatorial optimization, Kubo, so quadratic optimization problem solvers that can be imprinted in your neural network graph, and then the relaxation of this neural network finds the solution for you. Similarity search, right, where you do k-nearest neighbor search in this massively parallel fashion, which has been shown to be advantageous on a bunch of applications, including olfactory sensors. Second, bio-inspired circuits. So there's a whole bunch of architectures and neural circuits that we know from neurobiology that solve useful tasks. Whether it's navigation task with place cells and grid cells and SLAM network, visual odometry, whether there's some action control networks or predictive coding architectures or, some inverse kinematics networks. There's a whole library of algorithms that we know from biology that work and that are useful for moving things around. So there are people who take those inspiration from biology and develop algorithms and apply them in technical systems, most typically in robotics. So, Guido de Kroon has this example with landing very lightweight 2-gram heavy drones and developing a vision-driven landing algorithm for them inspired by, some vision of a bee based on the divergence in the visual field. There are some navigation algorithms used by a startup. So for real mobile robots used in retail and logistics based on ant navigation algorithms. The ants, they look at the horizon, it seems, and or can orient themselves based on pattern matching of horizon lines. And then there's very famous older work on rat SLAM, simultaneous localization and mapping, inspired by place cells of a rat and the adrenal cortex used in robotics. Almost done. And so on and so forth. So this is an example of a conventional algorithm such as half transform or a PID controller running on a neuromorphic chip and leading to immense savings in latency. And these are the more complex frameworks where maybe I don't go in for now. Just to flash them, that there are other algorithms out there that are massively parallel, that require support for massively parallel hardware, which are not deep learning. And then in my group, so that's what we do. We take different sensors, partially asynchronous, these event-driven sensors. We develop neural architectures which are not deep learning based. We also develop controllers for robots and try to enable new type of robots that can work in dynamic environments close to humans, where speed of perception is very important. Right. Yeah, that's it. That's our little group in Wädenswil by Zurich. I'm happy to connect if any of you got interested. Thank you.
Wow, thank you, Julia. You covered a lot of fields
Thank
in
you.
one presentation. So that was impressive. And so now we have time for a couple of questions. So please raise your hands in the audience. In the meantime, I was wondering, Julia, from your perspective, what is the timeline for when these neuromorphic computers will actually appear on the market and become useful for us?
So the ones that come from big companies like the Intel ones or the IBM, they're very close, right? So I think IBM just went for applications that are not for mass market, but they have a working chip. Intel also has a working chip. They decided not to go on the market with Loihi 2, but wait for the Loihi 3. That just gives them some more time to do some more in-depth research. But chip is usable. The startups are even faster. The SynSense chips one can buy already today. They're small scale. They can only do pretty simple tasks, like detect 3-4 gestures, for instance. But they can do that today in products. They already do that in some toys. They need the scale for their products. And there are a bunch of other startups. Brain chip with their Aikida chip. They also have a product. They don't do chips themselves. They only sell IP, and then you should build the chip. Yeah, so I think the chips are there. They're looking a little bit, they're like hammers looking for nails. So they look for killer applications where they really will be needed. I think it's good to have different technologies out there so that the applications can look for, find the right hammer for them. Yeah. So I think that's maybe the future. Not that the new neuromorphic chip will come and replace all the GPUs on this planet or be the next GPU. I think this diversity of different computing systems is what we should aim for.
Okay. So killer app, that's what's needed. All right. Any more questions? Well, if not, let me ask you quickly also again. So the epic question, because you focused a lot on what is neuromorphic and what is not, etc. But how our community could support your developments and also what you could offer maybe to Epic members.
So as Bert also said, in these neuromorphic chips, I think optical elements could kind of facilitate the interconnect, because for us, connections, short-range connections, long-range connections is everything. Full optical computing would also be fascinating. So there could be some elements, some reservoir computing, some recurrent networks that could be implemented in this optical way. What we could offer is maybe these algorithmic frameworks. So I think it would be interesting to look into, the algorithms that we are interested in. We are people in robotics. I think robotics is a very interesting field where latency matters. There are a lot of different types of compute that is needed, and a lot of needs for different hardware. So I think it could, on one hand side, be inspiring. On the other hand side, there are some ideas that help us use some unconventional hardware, which maybe has some, stability issues or reproducibility issues, but there are algorithms that can operate on such hardware. Yeah, so I think on this algorithmic level, there could be interesting discussions.
I see. Okay, well, thank you very much. If there's no further questions, let's thank Julia again. And we switch to our third speaker of today, Mikhail Kistner, the co-founder and CEO at Photonics. And Mikhail will talk about building a fully integrated high-performance computer.
Awesome. Thank you very much, Ivan. Yeah, so the goal of this talk is to talk a bit about how one could build a high-performance computer here in Europe, because at the moment that's not possible, right? Every high-performance computer has chips that are made either in Taiwan, that are made in South Korea or the US. There's no high-performance computer can actually make all the chips in Europe. And that's a bit sad, right? We have this great technology here, and yeah, we want to change that. At Photonics, that's our big goal. We want to build a general purpose high performance processor where everything is made in Europe. And when I talk about high performance computing or general purpose, I'm not talking about analog computing, right? We heard a lot about, let's call it this analog or this non-conventional way of computing. We use a very advanced technology, but to build classical old school digital computers. And that's a bit something that's often confused, because people, when they hear optical computing, they immediately think of the vector matrix multiplication world. That's not what we do. We actually build optical transistors. We actually build optical memory. And these two things allow us to build a regular CPU, and our processors, they execute code. So they execute standard C++ code. They can execute Python code. It doesn't matter. You can run anything on our processor, which includes AI, but is not exclusively for AI. So yeah, a very general purpose device. And we've actually already done that. We've already built an all-optical general purpose processor. We have all the components that we need, and it's currently all up to us to create a new computer revolution. And I mean an old school computer revolution in the sense of, let's build an all-optical version of a GPU, a CPU, but make it here in Europe. And if you look at the current field, right, we of course have to compare ourselves to the existing electronics, to the existing CPUs, GPUs, etc., which are of course Intel, Nvidia, AMD, and all these guys, and they do everything electronically still, right? It's changing. So they have their electronic transistors doing the logic, right? They're doing the arithmetic using digital transistors, and of course they're moving data around electronically and have electronic memory. Now, the trend is, of course, to replace the interconnects with optics. We've heard about that just now also, right? That interconnects are moving to optics, which is great. We love that. But in the end of the day, if you're not replacing the electronic transistor or the electronic memory, you still have this conversion step. So you're constantly converting either between the interconnects or between the arithmetic, right? If you're doing something like matrix vector multiplication, which is kind of, yeah, to us, it's a bit sad that you lose all the efficiency you have in the photonics by constantly converting back and forth. And that's where we come in. At Photonics, we are doing exactly that. We are replacing the logic and the memory by all optical components. That allows you to always be in the optical domain, and we really mean always. So the data comes in optically through an optical network signal. We process it optically, we store it optically, we do things to it optically, and then send it back out optically through the network interface, meaning there never happens an electronic conversion in our system. And yeah, the reason why we want to do that is, of course, as we heard, the memory bottleneck. Modern GPUs, they're very fast, right? They have huge amounts of compute. All the modern devices have huge amounts of compute, petaops, right? Really nice. But then you see, okay, wait, it only has a terabyte of memory bandwidth. That's a bit strange. And this actually leads to a huge bottleneck that you can actually do 1,000 compute cycles on 1 byte of memory. But what you're going to do with that 1 byte of memory, right? It's a bit sad that we have this huge gap, and it's called arithmetic intensity. So electronic devices simply have an extremely high arithmetic intensity, which is not a good thing. High arithmetic intensity means you have to do much more compute while you wait on memory. The ideal arithmetic intensity is 1-to-1, and that's exactly what optical computing, if you do everything optical, allows you to do, because now you can do one compute step, fetch memory because you don't have any bandwidth issues, you don't have any memory latency issues, and then you can compute your next step, right? So it's always 1-to-1. We always access one piece of memory doing one compute cycle, which is really nice and allows us to actually increase this performance. Okay, this was a quick rundown of Photonics, but what I really want to talk to you guys about today is chips, where they are made, where high performance computing is made, right? We all know that the USA, especially Intel, is making their chips in the USA. Samsung, TSMC also starting to build high performance computers in the US, but we recently heard from, for example, Nvidia, that they're not going to make them in the US. They're still going to make them in Taiwan. So Taiwan, TSMC, huge chunk of all the high-performance computers are made there, and that is not about to change with the current approach we have to computing, right? With even if we do something like, if we do something like in-memory compute, if we do very advanced matrix vector multiplication in photonics, right? All these have an electronic CPU doing, for example, the activation function or doing some other lifting, which means you can't really build a fully European high-performance computer. Now, of course, China is also trying to build their own line for high-performance computers at SMIC, and then we have Samsung, who are the only ones who can build these advanced nodes outside of the typical US-Taiwan space. Good. So if we want to build a high-performance computer based on optical digital computing, how will we actually do that, right? We all know modern NVIDIA devices have billions of transistors. Modern Intel devices also billions of transistors. Optics is very large. Our optical transistors, we're not talking nanometers, we're not even talking micrometers, we're already in the, like almost in the millimeter range, right? So it's a huge device. Also, our optical memory cells, much bigger. The idea is, hey, let's move away from scaling using quantity. Let's move towards scaling using quality. And that's really the whole idea behind photonics, right? We don't scale by adding more transistors. We scale by adding more wavelengths. We scale by adding more time multiplexing, and all these things that really allow us to increase performance without increasing the actual size of the chip. And that's really what we're all about. So, but how can we still build a CPU? How can we still build a GPU if we can't even make 1 million of these devices on a chip? And the simple answer is you don't need that many devices. It's a very common misconception that a CPU needs billions of transistors to do modern tasks. That is completely wrong. You can run a modern operating system on a CPU that has just a few thousand transistors. That's absolutely no problem. In the electronic world, it just means you're sacrificing speed. And I want to show you how that works. Because this is a typical electronic CPU. It has 8 cores. It's a Zen processor by AMD. And you will see that a lot of these things we don't actually need. We don't need the memory interfaces, right? We just send the optical signal directly to our optical memory. We don't need 8 cores. I mentioned, right? We scale through quality. We scale through a single core, meaning we can reduce that. So now we're already down to 10% of what we actually need to implement. Okay. Now, I mentioned we have perfect arithmetic intensity, which means we don't need cache. We don't need cache, which is a huge saving on the floor space. Now we're down to a few percent. If we don't need cache, right, and if we don't need any advanced things like floating point for now, right, let's do everything with integers. Then we can also completely remove any optimization features. We remove branch prediction, we remove operand forward, all these things that an electronic processor needs to lessen the blow of the von Neumann bottleneck. We just throw it out of the window because we don't need that. And suddenly you're in the range, hey, wow, okay, we went from billions to now 1 million or a few 100,000 transistors. Can we go further? Sure. We don't need all of those thousands x86 instructions, right? Those are all just optimization instructions. We don't need them. We can reduce it down to a reduced instruction set architecture. And of course, since we don't really need to be in the 64-bit domain, we can go to the 16-bit. We can even do a 32-bit processor. That doesn't matter. It helps us reduce the transistor count down to a few thousand. And that's really what optical digital computing is about. Using a design almost from the 70s, right? And making it run at terahertz, multiplexing it using multiple wavelengths. And then we get very energy efficient system because we only run a few thousand transistors. It doesn't matter if they run in tens of milliwatts, right? That's perfectly fine because we only have a few thousand and the processor is still more efficient. We have extremely low latency because essentially we can't really stop the light, right? So it just flows through our system and we know exactly how fast it flows through our system. And it allows us to build everything in Europe. This really brings forward the European photonics community and allows us to make the first high-performance computer fully here in Europe. And we already have the supply chain, right? We have the most advanced packaging houses here in Europe. We have the most advanced photonics integrated circuit manufacturers here in Europe. So let's leverage that and make a high-performance computer here, which has a few other benefits. Of course, it's somewhat electronic warfare resistant because it's not electronic, right? You have deterministic computing, meaning it's suited for real-time applications, like for us, right? Our first processors will be in airplanes. So these processors can be used in safety critical environments. You have minimal heat and EM signatures, which is great if you're thinking about any sort of biophotonic applications, etc. And of course, the material platform is as robust as electronics, so we don't have to think about it being super fragile, right? Since everything is integrated, we don't have to deal with lenses. So going back to this picture, let's add another box. Let's add a European box to this picture. And that's really what Photonics is all about. And yeah, looking forward to your questions. Yeah.
All right, nice, nice mission, Mikhail, and a nice presentation too. So let me immediately ask you, how can our EPIC members participate in your mission and help you building this HPC?
Yeah, it's actually quite simple. So it's all to do with the box down below, right? Build a great European supply chain for photonics. Don't move your photonics outside of Europe, but why not keep it here?
Okay, that's a good motto. We'll try to do that. And also, yeah, please don't hesitate to reach out to Mikhail if you have an idea of how to support him. Is there any more questions? Okay, let's see, Amir, go ahead.
Okay, this is a sort of amazing presentation. I was blown. A few questions. First of all, I mean, like sort of at a very high level strategic. I mean, kind of one of the plagues of integrated, photonic system is that they have a very narrow temperature operating window. So you have to always spend a lot of, also energy to actually temperature stabilize them. Of course, photons are not small. I mean, can you tell a few words about this in sort of temperature stabilizations and how does it compare in terms of whatever flops per second as a side-by-side comparison? Second is like, what is the main components do you need to actually build this sort of course, lasers is a no-brainer and detector, but can you tell like what is your pain points in going to higher speeds?
Yeah, so that's a very good point. So stability is of course very important. But one of the good things is if you work in the digital domain, you're not too affected by that, right? You only care about high and low values. If it's a 0.9, if it's a 0.8, it's still considered a high value, right? If it's a 0.1 or 0.0, that's considered a low value. Whereas in the analog domain, right, you really need very sharp values. So you need extremely precise temperature control. For us, yeah. It's nice that it's within a range, right? So that we can differentiate the signals, but it's not too big of an issue for us. And the power that we lose for keeping the temperature in this certain range is minimal compared to what an electronic processor would need in cooling, right? So it's still much better than that. And regarding components, yeah, that's a very good point. Since you're from Lithium, yeah, we need exactly that. We need non-linearities. That's extremely important for all optical computing. You can't build a digital optical transistor without a non-linearity, and that's something we need on a PIC platform. And yeah.
So second order non-linearity is the most important thing that actually would require.
Second order, third order, we also care about things like saturable absorption, saturable amplification. Basically, any type of nonlinearity allows you to build an all-optical digital transistor. I say transistor, an all-optical digital switch in that sense.
Okay, good. So that answers your question, Amir, I guess. All right. So thanks again, Mikhail. Great presentation, great mission. Before we go to the next talk, I'd like to mention that actually our meeting is also supported and sponsored by Scia system. And we have Manuela with us that would like to share a few words about Scia systems, right? Yeah. Manuela, yeah, you need to unmute. And yeah, so this is our EPIC member from Germany, and they produce wonderful systems that Manuela will talk about quickly.
Yeah. Hello, everyone. I don't want to steal too much of your time because I know all of you are very interested to get all this detailed technical information from all the other participants today. So I am Manuela Löth from Scia Systems. We are a company located in Eastern Germany. And what do? We basically do manufacturing of equipment for plasma and ion beam processes. So all the devices, everything you finally use to generate all the know-how relies on process equipment that does deposition, structuring, and so on. And we, as a company here, we do exactly that. So we offer special equipment that is needed for the special requirements optical components have, or all those other equipment, all those other components. We have basically two things I want to highlight today. So basically we do, with one of our tools, we do dimensional corrections. So if you have very tough requirements for layer uniformity, you have a certain deposition process, it is leads to very non-uniform deposition, then we can use a focused ion beam to correct at certain positions the thickness to improve uniformity. This can play a very crucial role for your applications. And this is one thing that how we can contribute to the manufacturing chain. And the second thing that we do is we offer ion beam etching equipment. So for example, for photonics integrated circuits, where you have very tough requirements for sidewall roughness and for sidewall angles, we can do that with ion beam etching. We have experience with all the materials that play an important role: lithium niobate, silicon nitride, silicon oxide. All there we have a lot of experience, and our tools can be used for that. And the most important thing is that we have demo tools at Scia Systems. So if you have any requirements on doing a demo, please feel free to contact us. We can for surely plan something here at Scia. That's it. Thank you.
Okay. Thank you, Manuela, for your input, and thank you for supporting our meeting. So keep in mind what Scia Systems can offer you. And let's switch to the next talk, which is given by Roberto Siagri, the CEO of Rutonium. And Roberto will talk about photonic gate-based quantum processors with multi-dimensional qubits. Welcome, Roberto. The floor is yours.
Thank you. Yes, the idea is to present today our approach to photonic quantum processor, and just using a single photon. The idea is to be able to enable the edge computation, not starting from the big infrastructure at the cloud side, but to the edge where data are produced. And so to be able to design small processor that can be in some way integrated inside embedded computers or edge computers. So we use a single photon to design the deterministic qubit, two qubit gates. The idea is to use the orbital angular momentum. In this way, we are able to represent many qubits inside the same photon. And this will remove the need for ancilla photon during logic execution. And not only that, we have also another interesting way to remove the error or the error correction that is based on a fault detection and without any measurement during the execution of the operation, but just at the end. This is, of course, compatible with silicon photonics, and what we want, and this was one of the reasons to design this, is has to be room temperature, no cryogenics involved in all the processing. And just two words about on the orbital angular momentum. It is a property of photons that is not used in telecom. And this, in some way, the result of the total angular momentum, that is spin momentum and orbital angular momentum. And in this way, you have many states that you can use more than just the spin state. And you can see that in this way, we can insert inside one photon at least two qubit using just the level 1 of the orbital angular momentum. This is the idea to build this deterministic 2-qubit gate that are essential for a quantum circuit. So with just one photon, we can design all the gates that are required to achieve an universal quantum computer, and without a need for ancilla photon during gate execution or no post-selection, and all linear optics. With this part, then we have the full detection that is using the symmetry breaking of the OM. And also in this way, we do not need to make any sort of correction with additional qubit. It is because these are flying qubit, we just repeat. We repeat, we measure and repeat, and in this way we can have the equivalence of the logic qubit with a physical qubit. So we move the problem on time. Instead to move the problem on having more qubits, we just move the problem from same qubit, more repetition. And of course, this is just an accelerator. So the idea is to combine this kind of accelerator with traditional computer. And in our roadmap, we have 3 form factors. A single chip, a desktop, and a down card, according to the use and according to our timeline in the miniaturization. So with this kind of things, we can move for instance, this is an example of an AI application at the edge, in which we have an hybrid quantum gun, and this is our last processor that is a 4-qubit processor. And with this, we can have a quantum generator and a classic discriminator. And we can dramatically improve the efficiency of the gun algorithm using this combination of classic and quantum. And the idea is to be able to move all these quantum and classic things where data are produced. So inside sensor, close to what it is, the edge of the network, and to have a much more intelligent edge. And just to show in terms of dimension, how big is this stuff now? The processor is, yes, as you can imagine, a small silicon device. Then it is packaged in a big package now. And then, well, it is just the detection stage and the generation and the single photo generation stage. And of course, now we are working to miniaturize the section 4 and 5. Now we are on the 4, and for the end of the year, we will have all the generation inside the chip. And then next year, we will move all the detection system inside the silicon. Just to recap, it's with this approach, we consider this a new step in quantum photonics. Of course, photons are great stuff, low the coherence, they can work at room temperature. The point is how you can create a deterministic gate with this. We have solved the problem of the deterministic gate with photons. And by the way, we are opening a space of infinite state space using the orbital angular momentum. At this stage, we just have 2 qubit, and we are moving at 3 per photon soon. And all this, there is a very well theoretical foundation. That is a paper from our CTO on how to use this property of light as a bosonic Majorana field. And with this, where this approach is unique, it's because of this twisted light that has many qubits in the same photon, because in this way we can use the natural entanglement of the state inside the photon. So, and that's give us the deterministic gate logic. And then we leverage this topological qubit in order to have a topological error detection. And this means that it is much easier to build this error detection and also handling the correction. And that's my speech is concluded. It's concluded.
Okay, thank you very much, Roberto. Great presentation. Very interesting developments you're doing. So let me, as always, ask you, where is the room for collaboration with our community?
Oh, a lot of room. We are looking for the point of managing orbital angular momentum require factories, Silicon Foundry, that has a very deep control of the geometry. The orbital angular momentum is not easy to manage. The geometrical things are very critical, and also the thickness is a little bit different from the thickness of the telecom sector. They try to avoid the multimode. We are in a multimode waveguide, and multimode waveguide are thicker than the monomode waveguide. So we hope that we are now producing here in Europe these things. I think that Europe has to invest more on the Silicon Foundry. We want to remain fabless, so we look for foundry first, and second, we look also for laser producer that has very small and compact laser. We just designed the source in terms of from a laser to a single photon. The circuit that is designed by us, but not the laser. So very small and compact laser. And then the detection section that has to be a room temperature. So the detection section has to be more close to what is a camera, a CMOS camera. So a single photon CMOS detector. And so that is another stage that it's for the next year, as I just said. So foundry, detectors, and laser. We take care of the source and of the circuit.
Okay, thank you, Roberto. Please take the note of this, everyone. And let's thank Roberto again. And we need to catch up with timing. So we switch to next speaker, who is Anna Gonzalez, the VP of Business at iPronics. Hello, Anna. Welcome. You can share your presentation, and Anna will talk about the optical switches, I believe.
Okay, hello, good afternoon. Now you can see my presentation and you can hear me, right?
Yes, go ahead.
So then I'm going to start. Thank you very much for the invitation. It's a pleasure to be here talking for the EPIC audience. First of all, I want to admit that we are not doing photonic computing, okay? We are doing something else. Is still related? Yes, because what we do is optical switching. At the end, we don't care about if the GPUs or XPUs are working in photonics or are working in electronics. We just process in optical. First of all, I would like to present to you our building block. What is the element? What is the core of our technology? So in this case, you can see here, this is a 2x2 multimode interferometer. You can see 2 input, 2 output, and we are building this in silicon photonics. So this is photonic integrated circuits, silicon photonics, and this is our tunable element. We are controlling this element using a thermo-optical phase shifter that allows us to reconfigure it in a microsecond reconfiguration time. Also, I would like to bring your attention that we are processing here in an analog way. So we can have this cross state, we can also have this bar state, But also we can also have this tunable coupler, which where we can just split the signal in two. We are going to get losses, of course, but well, this is a beam splitting of our signal in the two output ports. By putting many of these devices, many of these building blocks together in some kind of a mesh arrangement, we are creating this photonic layer. And all these thermo-optical phase shifters are controlled by a software, a dedicated software through the control electronics. So at the end, what we have is this one URAC product that we can use in data centers. Many of you will remember when we started at Ipronic, we started doing a photonic FPGA, right? A photonic field programmable gate array. It was literally this. So what we were doing is to put all these elements in an hexagonal configuration. And with this type of devices, we were able to do whatever. So we were able to do filters, infinite input response, beam splitters, delay lines, any kind of photonic functions with some limitations, completely controlled by the in-house developed software. And we were also thinking about photonic computing. The issue was that we were running again and again the simulations, and we were seeing that with this, in particular with this configuration, we were not going to be competitive against an NVIDIA GPU for many years. So we really need to increase the integration of these let's say, to reduce the footprint of these elements, increase a lot the functionality per area in the chip, to be able with this type of technology to develop a photonic computer. But I see there are other mechanisms, right, able to do it. So then what we decided to do was an optical switch. So in this case, what we have done is that we have optimized this general programmable technology to develop an optical switch. In this case, in data center applications, it's going to be very important that it's lossless. So we added an disaggregated optical amplification step. The device is going to work in the entire O-band. It's designed to have a very flat response, a spectral response in the entire O-band. No electro-optical conversions, right? We process in the optical domain, and right now it has 32 radix, so 32 input, 32 output port, but we are planning extension of this running in the next periods. Fast reconfiguration time, low latency, right? The speed of light, and then we have developed a dedicated application programming interface. So now it's perfectly compatible with software-defined networks, and it can be controlled. You can control the device, that is layer 1 hardware in a data center, using the control plane, the same control plane that you are using for the rest of functions. Also, because it's photonic integrated, you can add some photodetector arrays. So we have photodetector arrays in the input ports, in the output ports of the chip, but also before the optical amplifier, after the optical amplifier. So yes, you can have completely control of the chip. Also, as I said, we can have this compensated multicast configuration in addition of the lossless point-to-point routing. Also, you can control the gain of the device. So it's not only that it's lossless, but also you can add 3 dB gain if it's interesting without impacting the bit error rate. Then regarding the telemetry, yes, so you can control everything that you want to control. And now let me just go through some of the applications. In data centers, we call scale out what is happening in the layers, like the spine layer, the leaf layer, top of rack. This is the scale out of the network. Scale up is when we are talking about what is happening inside the rack. So we already, well, it's not that we identified, it's that the industry has identified a couple of applications for this scale out. In this case, the first application will be this failure resilience. This slide is based on an article from NVIDIA where they are using some of these MEMS-based devices for this failure resilience. So in this case, what they are doing is that they are connecting some of the ports of these OCS that are integrated between the layers of the data center with an spare switch. It can be also an spare rack. So then they recreate a failure in one of the NICs. And after this failure, they are able to reestablish the connection in 4 seconds. This happens because it's a MEMS-based device, so then it took 4 seconds. With one silicon photonic OCS, this will be much faster because they reconfigure much faster as the one that we are developing. Another important application right now is to be able to reconfigure the physical topology of the data center. So you can adapt it to different traffic demands. So in this case, well, as you know, these data centers are optimized right now for all-to-all traffic. But however, actual traffic patterns, they are showing spatial and temporal structures. With using an OCS, you are able to change this topology on demand, and this will be controlled by the SDN control plane. Finally, the scale-up networking. So what happens when you put OCS inside the rack? In this case, you can really increase the domain of the GPU, so you can put more GPUs inside your rack, increasing the efficiency of the training and reducing the time that is going to take. And in this case, you don't really need such a big radix OCS, but with a small radix OCS like the one that we are developing now, will be more than enough and more cost efficient. And just to finalize, this is what I was mentioning about the multicast. So because we are doing this analog operation, we are able to split, and even we are not even splitting 50-50, right? We can do 20-30 or whatever proportion that we want. And in this case, it will have a big impact if applied. It has a big impact in these strategies for training that like the data parallels, and we'll be able to do these data parallels without adding latency and reducing a lot power consumption. Yes, and that's it. Thank you very much. And if you have any questions, don't hesitate to ask.
Okay, thank you very much, Anna. Great presentation as always. Any questions from the audience? Okay, if not, let me just quickly again ask you to answer the epic question about the collaborations, and we need to catch up on timing, so we go ahead.
Okay, yes, I am familiar with the epic question. So, okay, so in this case, we are also fabless, right? We are doing the assembly in-house of the different elements, and we are also designing a lot. So our main teams are the software team, the team developing the application programming interface, but also the photonic team. So first of all, we will be very interested as well in fabricating in Europe. To have to go to other places to fabricate is really a handicap. So all the services and fabrication of silicon photonics that can be done in Europe, we will go. Right now, it's not possible, but if there is this possibility, we will go to fabricate in Europe. Then whatever packaging able to reduce in edge coupling, you know, from the fiber to the edge, I don't know, any technique able to reduce down 1 dB losses per facet will be very welcome. And what else? We are also designing optical amplifiers. So companies working on optical amplification, yes, we are also interested in connecting.
Okay, very good. All noted. Thank you, Anna, again.
Yep.
And we switch to next presenter, who is Jörg Smolensky, the Business Development Manager at Nanoscribe. Hello, Jörg. Yeah, you need to unmute. And yeah, I'm sure Jörg will talk about the wonderful machines that they produce at Nanoscribe. Yeah, we still don't hear you, Jörg. You need to unmute. And then the floor is yours.
Yep. Okay. Hello, Ivan. Hello, everybody. Nice to be back again with EPIC in an online meeting. So I'm going to talk today about what we can do for optical computing. Basically, we can print micro optics to have lower loss of coupling. This is a little bit based on a project we have right now. It's called the Phoenix project with a couple of partners. IBM, one of the speakers here, is also involved in this project. The motivation is basically that the AI demands a lot of computing power. You have digital electronics who struggle to satisfy with this. So photonics is a possible additional solution. It's not the only solution. Electronics will always be there, but it's a possible solution. Just very quickly to who are we, Nanoscribe, those who still don't know us yet. So we are not a startup anymore. We are an industrial the company right now. We are 100 people, close to Karlsruhe. We have offices in Shanghai and Boston, several patents to support our technology. And this is just look into our one of our process development labs, where we have some colleagues doing some studies for feasibility for different applications. What is maybe not known in this area group here of people is that we, since September, so now 6 months, we are part of the Lab 14 group. Lab 14 is not known very well outside of Germany, as far as I'm informed. So basically, one of the most known is probably Heidelberg Instruments. So we are now together with the Heidelberg Instruments. I think that's going to be very interesting for the future. But coming back to the subjects, so what we can do, we can print optics and enable enhance photonic packaging, bright connections, lower losses. So we can use our technology, which is kind of 3D microprinting. It's based on 2-photon lithography for photon integration in a large variety of application. The main application right now is here quantum computing and optical computing. So this was well presented already by previous speakers previously. And how can we do this? Basically, we have a femtosecond lasers, we have scanning mirrors, and we concentrate the light into a resin. And we can also additionally, not only concentrating the light, we can also, with our patented grayscale technology, we can tune the voxel very, very quickly at 100 megahertz while scanning. So instead of having, for printing optics to enhance the coupling, having tens of slices to have a very smooth surface, we can do a single slice and have this intra-sliced tuning of the voxel, which helps to have optical quality and then very low losses for coupling. So coupling, what do you want to couple? What do you need to couple? In integrated photonics, you couple from a waveguide to a fiber. So you have seen the difference here. So you have this waveguide in the simulated electric field here. So that's 200 nanometer. And if it's at scale, look at a single mode fiber, 1550, 5 microns, you see what is the difference. So if you would just use this and couple to each other, you will already have minus 7 dB loss. You don't want that. So we can basically print an optic to match these different mode fields. So focusing or collimating depends on what you need. Additionally, especially the 1 dB ratio, when you position two optical waveguides or optical elements next to each other to couple light, you can say roughly that's a quarter of the mode field diameter is the lateral tolerance. So for a 5 micron or 10 micron diameter single mode fiber, this would be 2.5 micron. You still will need some very precise positioning systems. We can do collimated lens coupling with 25 microns, and you add some 7 microns and more. So we can expand the beam. In the project I've mentioned, we have shown this at different locations. So one location is basically fiber to chip coupling. You can see this in the scheme here. So that's between the ENP and the Photonics PIC device. So for this, we use our in-house software where we can add, do the design of a fiber array, basically. We can have the design of the collimated lenses. You just enter the lens formula. This is the orange part. Then you can say, this I want to have in optical quality, this I want to print fast, or I want to have good adhesion. So there are a lot of standard recipes already included in our software. And then you can do the collimating lens on the fiber. You can do this in batch processing. On the other side, on the chip sides, again, we can enter the lens formula STL, and we also can very precisely print the lenses by the scanning mechanism, but also we can detect. So we use you can see here on the upper area, let me quickly put on this laser pointer. So we use double square or circles or crosses, whatever you want, fiducials on the chip to detect where is the waveguide. We can also detect the waveguide, but that is not as precise as if you have fiducials, or it basically will take more time. Most of the time, fiducials are sharper in detections, and then precisely position to these fiducials the optical lens. So we adapt the optical, the shape of the optics, the printing of the optics to the edge and to the position in 3D of the waveguide. Also, basically what we have in-house is a simulation for these kind of optics, as you see here on the upper area in X and Y. We have a tool for measuring these beam profiles for certain wavelengths. 1550 is clearly possible, green light too. And then if you look at the overlay, you can see there's nearly no mismatch. It's perfectly. So this is basically the best way to couple between different optical platforms. Here's an example. So we coupled from a fiber to a PIC chip. And in this case, we had 1.3 dB, not the 1 dB, Anna, I'm sorry yet, but we can go there. So we can maybe discuss about that offline or in another call. You can see here also some print times. They are not yet fully optimized, but so 2 minutes per lens on the SOI chip and around, as mentioned already, 45 seconds per lens on the fiber side. This is a larger view. Last but not least, we can not only print beam shaping optics, but also imaging optics. So this is from a design from Print Optics, a customer and partner from us. And this is for endoscopes. So, and we have other colleagues who have done optics for optical arbitrary momentum. Please don't ask me how this has been done, but a previous speaker mentioned this. We can discuss about this, or I can put him in contact with my colleague who has been doing the design. So the technology opens wide possibilities for printing different elements, optical elements, and other things. Last but not least, we can do this scalable and at high performance. You see here the technical specs which are possible for the optics in shape accuracy and surface roughness. We can do batch processing for fibers. We can do batch processing in trace on gel pack of single dies. We can do it at wafer level if it's required and makes sense that you always need to look at. Yeah, so we offer this for photonics industry. We have a couple of awards we achieved. This is for having high quality, faster production. And as I mentioned before, we do the software, do the hardware, we do the printing materials. We bring it every year, it's a new printing material. And we are located here in this nice building. So if you are interested and you have a challenging project, contact me and we can see if we can help you with our system to solve it. That's
Great. Thank you
it.
for a very good presentation, Jörg, as always. Yeah, well, my 1 minute for questions, if there is any. Okay, Francesco from Enea, please. You need to unmute, Francesco.
Okay, thank you. What is the typical laser do you use to realize this kind of structure?
We use a 790 nanometer femtosecond laser.
So may you repeat the frequency, the wavelength, sorry?
790 nanometers. So it's in the infrared, but the reaction, the 2 photon absorption is in the UV.
Okay,
so it's yeah.
Thank you.
Okay, no more questions. Okay, in this case, I think Jörg again, we need to catch up with our timing. And last but not least, we'll have a contribution from a bit more of a software side. So Ksenia Bogomolets, the CEO of Quantix Security and Coding, will enlighten us about their developments. Thank you, Ksenia, for joining on such a short notice. So looking forward to your presentation. Yeah, you can now share your slides. There's a button at the bottom to do this, and you can unmute.
Okay, yes. Hi. So that's the first remark. So I'm in the meeting with two devices, yeah, because I don't have access to the microphone on one of my devices. And about the software, yes, kind of, but it's more about security analysis and preparation for certification, but you will learn more in my presentation.
Okay, looking forward to that.
Yes.
And yeah, once you're ready, so the floor is yours.
Yeah, I'm looking for that's this one. Share. And start from slide. Yeah, okay, the title is Validation of Photonic Quantum Devices. And yeah, we are a small company, like an SME, even micro SME, European, based in Germany, and we exist since 2019. So yeah, we are a family business, only 7 employees and 1 permanent freelancer, 4 ladies and 4 lads. No, now actually we are 4 ladies and 3 lads. The main income comes from information security consulting, and we have 1 research and development project funded by the German government called QuantID, and I want to tell you more about what we do in this project. So the project scope is quantum secure digital identities. It's a highly interdisciplinary project. Our partners are Fraunhofer Institute for Photonic Microsystems, MTG AG Darmstadt, and the University of Regensburg. So Fraunhofer actually does the hardware development part, and the University of Regensburg and us, we do the validation and design requirements, help defining the design requirements of the QRNG built by the Fraunhofer EPMS according to BSI and NIST criteria. It's a very interesting project. Yeah, we are also the project coordinator, and we learned a lot in this time. So first of all, why do we even have to do this? Quantum mechanics is the base for perfect randomness, or true randomness can only be quantum mechanical. Any other random number generator will produce deterministic outputs, even though if they might be, let's say, very complex deterministic systems. So that's what in particular physicists know. Now the validation of true randomness is a very complex topic. We also underestimated it before the project, but never mind, that's what research can be. And that's why I said we learned a lot. And due to this fact that the validation of true randomness is very difficult, there is still a very agitated discussion between physicists and information security institutions or organizations. And we try and help to bridge that gap. Yeah. So, you know the use cases for the true randomness from quantum mechanical systems. We have quantum random number generators and quantum key distribution, and both are highly interesting for information security. Yeah. So in practice, it is difficult to prove that a device is truly based on quantum mechanics alone. Yeah, there are both classical and quantum noise in an output of a device, which is based on quantum mechanics, and the methods to identify this noise is the thing that we are developing in this project. So we looked at two evaluated two photonic sources. One is the phase noise, the other one are vacuum fluctuations. And we are sticking with vacuum fluctuations because after interaction with the community and several publications, we said that vacuum fluctuations are more promising for highly performant random number generators that could be deployed to industrial systems sooner than phase noise. So, the physical properties. True randomness, which causes unpredictability, is something that is highly desired in information security, not only cryptographic key generation, but also other applications want to have true randomness, like identity access management protocols demand high entropy sources. Yeah, and another nice property is, of course, that the manipulation of the system is noticed. Yeah. This is in particular also interesting in cloud environments where we have like shared hardware and a virtualization on top. And yeah, it is actually not easy to really be sure that no one knows the key that you are generating in the cloud. Good. Why is the true randomness so important? Yeah, the unpredictability of cryptographic systems is ensured either by algorithms. The pattern of the data transformation must not reveal any property of the clear text, and the cryptographic secret must not be predictable. If it is predictable, the most secure algorithm does not help. Yeah, this applies to all kinds of cryptography, symmetric and asymmetric. So that's just about the use case. I think this is not so new for you. Yeah, there are many QKD networks already established across the world since many years. However, the evaluation and certification by official information security bodies is not as well progressed, has not as well progressed. But by now, we have the functionality classes for random number generators by the BSI, who gives you the opportunity to classify your QRNG according to BSI functionality classes, which is a good thing, actually. Yeah, we asked them also if they plan to have an own standard for QRNGs, but they don't in the next 10 years. I must say, when I created these slides, we were not as far progressed as we are now. And so I will talk a little bit more from imagination. Yeah. So there is a big difference between NIST certification and BSI certification. And that's the stochastic model of an entropy source. And the modeling of an entropy source is actually the base of differentiating between quantum mechanical noise and other noise. And that's critical in really differentiating a quantum random number generator from another random number generator. And that's also why we want to go this path. And yeah, also another remark is that the source, this term, the source for the BSI is the whole setup from the actual photonic device until the ADC, analog digital converter. And so any component that is within that device until the ADC is considered as the source and needs to be considered in this stochastic model. Yeah. Okay, so that's from my side. What can we do for you? If any of you plan on designing and creating a quantum random number generator and aim to go for certification, our company can help you with that process. Yeah, that's what I can offer here. Okay, so thank you all.
Thank you, Ksenia. Great input. You mentioned what you can do for you, but you never mentioned what our community can do for you.
Yeah, okay. What can your community do? If any of you have ever built stochastic models for photonic quantum devices, that would be interesting for our project, like to have an exchange. Yeah.
Okay, great. This is noted now, and yeah, thank you again for joining us on the last minute. And yes, so I think our meeting is coming to an end. Let me just share a few brief slides with you. So first of all, this was again the online technology meeting on photonic computers and AI, presented to you by EPIC and supported by our sponsor Scia Systems. Second of all, thanks again to all the speakers of the session today. So Bert, Julia, Mikhail, Roberto, Anna, Jörg, and Ksenia. So thank you very much. This is an unforgettable meeting, and I'm sure we'll follow up on this topic in the future. So let me remind you that EPIC Photonic Industry Consortium is there to consult you on the technology and market studies, on the networking opportunities, providing you support with mentorship, recruiting, and investment. This is only possible due to our EPIC team that you see on your screen. And this meeting we have here is the last online technology meeting before we go to Munich, where we will be part of the Laser World of Photonics Expo that takes place at the Messe Munich on the 24th and 27th of June. And EPIC is also the organizer of the integrated photonic application stage there in Munich, which means we will hold a stage in the middle of the expo floor with a very strong agenda of speakers that will all talk about the applications of the integrated photonics. So yeah, mark the date and please join us there in Munich. And also consider joining us later in the 1st or 2nd of October in Denmark, in Copenhagen, where we'll have a technology meeting of EPIC dedicated to quantum technologies. It will take place at NKT Photonics, and it will take place in Copenhagen the same week as ECOC, so you can join both events in one trip. So mark the date and hopefully see you in the beginning of October in Copenhagen. So with this, I'm glad to close the meeting and thank all of you for your attention and participation. Thank you and see you on the next occasion. So you will have now also the poll on your screen. So we'll be also thankful for your feedback about this meeting. And yeah, so the room will be open for a few more minutes in case you want to exchange contacts or chit chat with someone in our audience. So now it's an open mic, and otherwise, see you on the next occasion. Thank you. Yeah, great presentation, everyone. And yeah, I'm positively surprised with the attention we got